God morgen og velkommen alle sammen til vår webinarserie God forskermorgen. Dette webinaret-serie er organisert i samarbeid av Multiconsult og Hydrogen. Dette er første episode i 2023. Nå videre en gang i måned kommer en forsker fra Hydrogen og presenterer sin arbeid til oss i bransjen. This presentation will be in English, so we'll continue in English. My name is Filip Patočka. I work in the hydropower section of Multiconsult, and I have a pleasure to present Birender Singh, who is a postdoctoral researcher connected to Hydrogen. Birender will share his research into how can non-destructive methods predict defects of the Stator Bar to us. If you will have any questions, please write them to the chat or we will take them at the end of the presentation, and the webinar is recorded. Thank you. And you can go on, Birender.
Yeah, hello, good morning, everyone. First of all, thanks, Patoka. Is it audible, Patoka?
Yeah, you can use Philip.
Thank you so much. So, good morning, everyone, once again. Like myself, Birender Singh, currently I'm working as a postdoctoral fellow with the NTNU department in the Hydrogen project. And the topic of my today's project is like how can non-destructive methods predict defects of the stator bar? So I'll try to explain things more in a simple manner so that it will be rather than it will be more in depth of the electrical. So like in the present scenario, currently we all are shifting towards renewable along with the reducing the carbon footprints by phasing out the carbon based our coal based thermal power plants, and also we are try to avoid to use the nuclear power plants also. So using this in this case, it will ultimately promote the more and more intermittent operation of hydropower plants, because with this more and more intermittent operation, we can achieve the power grid system stability and maximize the earnings. So what is this frequent start and stop operation? Hydropower plant usually take very less time to come into the picture as compared to the thermal power plants. So for a sudden increment of the demand or sudden we have to shut down some load. So these hydropower plants, like these small hydropower plants, can come into picture in a very short period of time. But these frequent start and stop operation will lead to a thermomechanical stresses to the components present inside the hydropower plants, and especially in the case of material which we are using around the windings of the hydrogenator power plants. So these insulations basically they have a different thermal coefficient of expansion, like insulation having a different, and the copper which we are using they having something different. So even literature also suggests that it was reported that there are various kind of damages are there. So around 68%, around 58% is damaged because of the insulation damage. I mean, these are the scenario taken care of the around 70 hydropower plants, hydrogenators, those in which out of 70 failures, 58% failures is because of the insulation damage, and 24% of the mechanical damage, and 17% is because of the thermal damage, and 3% is because of the bearing damage. Now this insulation damage will also further consider of further different reasons why this insulation is getting deteriorate with time. So there are several reasons. One is because of the initial partial discharges that plays a major role around 22%, and the contamination of the winding, and the aging of the insulation, this 30, which takes a more amount, around 31% of the damage is because of the aging, it's because of the time it get damaged. And the second thing is loosening of bars in this slot. I mean, I'll explain in the next slide how this loosening of bars in the slot, how this partial discharges, and how this agings are affecting more to the insulation failure. So I'll show some pictures like how these failures occur in the, like there are several failure reasons. I mean, in insulation failure, it is not because of a one particular reason. I mean, there are a multiple type of stresses, and that take place in a synergistic way. I mean, it's a like simultaneously combination of several different effects, like it's because of thermal effect, because of electrical effect, because of mechanical effects. So it's not a single effect which will take place to the damage of the insulation. So these are the some gaps are there near to the copper strips and inside insulation. So I'll explain this, like these are the 15 copper strips, and around this we are having a insulation that is of epoxy and mica insulation. Now this epoxy and mica insulation during the frequently start and stop operation, in which the temperature of these insulations and copper strips are like changing from 40 degrees Celsius, or we can say from ambient temperature to the upper limit of that particular class of that insulation. It's near about 110 degrees Celsius, 130 degrees Celsius. It depends upon the class of what type of glass we are using. Now, the expansion of this material and expansion of this material and contraction is different because of they have a different coefficient, thermal coefficient. Due to that, there might be a chance of some gaps will be formation inside the insulation or near to the copper endpoints, like conductor. This is our conductor, copper conductor, and near at this point we having some gaps. So these gaps are called as like because of the delamination of the insulation. Another point is like in the slot where we kept all this entire winding in a particular slot of that hydrogenator, in a particular slot of a stator. Due to the mechanical movement of these stators, there might be a chance of a abrasion around the outside of the surface of the insulation. That will also cause the deterioration, and which will further lead to the breakdown of the machine. And if the gap between the two nearest bars, the gap between these two nearest bar is less, then there might be a chance of bar to bar discharge. So these are the reasons like which will ultimately lead to the failure of the insulation. So for my study, like there is a nearby small hydropower plant in Uvre Fiscomfos, and which where that hydropower plant was commissioned in 1976 with the rated active power of the 7.6 megawatt and the nominal spanning of around 3.2 kV. So, and that the turbine was manufactured by the Quarrer, and the generator was manufactured by the national industry. So in the next slide, I'll give you some pictures idea about that, the size of the stator. I mean, like the windings, what I'm going to use for the testing purpose. So this is our stator part, that is the outer part, and inside this we are having a slots. These are the slots, and in each slot we have kept this type of long stator bars. These are called as a bars. If a single this black color if I taken, that will called as a bar, and if I take it complete one circle of this, called as a one coil. And this is the rotor part which is inside it for the that will take as a rotating part. That's why it is called as rotor part. So just one second, yeah. Now at this point, this type of slots are there. Like these are the laminated steel core, and in each slot we have kept these windings. And this upper these things are the wedges. If these wedges are like with time due to the mechanical movement, these wedges are if loosened, then this will start loosening and it will start moving inside this slot and will cause the abrasion to this winding. So they are tightly packed inside this slot so that there should not be any small kind of, even there might be a chance of discharges between this, because this is at ground potential and these windings are at high potential. So there might be a chance of discharges even inside these slots. Because of abrasion, that insulation also get damaged, and that will ultimately lead to the small discharges inside these slots also. That is called a slot discharge. So now to in the next slide, what are the terminology which I'm going to use in this presentation? Like this one is coil 1, which is called as a backup coil or pristine coil. The another two, coil 2 is the serviced coil, and the coil 3 is the dummy coil. So basically three different coils I'm going to use. All these coils are manufactured at the same time in 1976. But the coil 2, which is the service coil, which has been in service for 35 years, and after its 35 years, we have taken it out. And if we want to go for any maintenance or further replacement, so for that we need to conduct some tests. So those tests are called as a non-destructive test. And these tests I'll explain in the further slides. And the backup coil, which is also manufactured at the same time when in 1970s, but it is not in the use. Like these coils are not in the use. They are simply just kept in some as a backup bar, which we called as a backup bar. And coil 3 is also not, it's also manufactured, but it's not in the use. And they basically coil 1 and 3 are not energized. This one is the already energized. But this coil 3, which I'm going to use, is for measurement of the temperature profile around the radial length of the stator bar. So at every 1 meter, I have kept some thermocouple sensors to measure the temperature profile of the insulation, and even drilling the holes and putting thermocouples inside the copper bars to measure the insulation and to measure the temperature profile of the copper also. So this is the way, like I'm going to connect these three coils. This coil 1, which is a coil 1 is a pristine coil or a backup coil we call as. Coil second one is the service coil, and the coil 3 one is the dummy coil. Now this coil is connected in series, and each coil is having a two turns. Like from here, we're going like that, and then this, and then this is one turn, and then again this is the second turn. So each coil having a two turns. So coil 1, and then it is connected in series with the coil 3, and again it's connected back to the coil 2, like that. So coil 3 is our dummy coil, which is not energized with the voltage. Only now actual what the insulation which we are using here, they are like they are facing the several different type of stresses. The one stress is thermal stress. Because of sudden start and sudden stop, the temperature will suddenly shoot up to 110 degrees Celsius, and then suddenly temperature will go back to the ambient temperature. So this temperature increment, this is like a thermal effect. Parallel to this, they are stressed by the voltage also. So what I am doing is I'm going to conduct a similar kind of behavior inside the lab and try to simulate the same environment. So this coil 1 and coil 2, they will be like stressed by the voltage and current. And coil 1, 2, and 3, they are only stressed by the current only. So because by the help of current, we will provide a thermal effect. So in the next slide, I'll show you this. This right side part I have shown right now, like this is only a thermal effect. We are providing only the thermal effect. So this current transformer will feed a current of near about 1500 amperes based on the rated values. And this current will create a I square R, basically that our ohmic losses. I mean, like if a huge amount of current will flow, but the voltage of this current transformer is like 2 volt or 3 volt or maybe one or 2 volts. It's the near about 1 or 2 volt. So basically it is not a voltage transformer, it is a current transformer. So it is only feeding a current at very low voltage. So basically this coppers, inside this copper, they are at ground potential. And these copper strips, like these insulation, these black color insulations, they are clamped in the two steel bars. So this is a steel bar. Inside that we have kept the copper strips. Now this entire setup is stressed by the current, and the temperature will shoot up and it will go down with the help of fan, which are controlled by the PLCs, which are externally controlled by the PLCs, and the temperature will range from 40 to 110 degrees Celsius or depend upon the class of the insulation. Now this one or two having some one another extra blue lines. Basically these blue lines are for, these are the connections for the voltage stress. Like one and two coils of the hydrogenator, they are stressed by the voltage profile of the rated value. So this voltage transformer, and in between this blue color dotted lines, this is a online partial discharge monitoring. What is partial discharge? This I will explain in the further slides. And this is a continuously online monitoring, which is like if while my conducting the entire test, I'm keep on measuring the partial discharges inside these windings. So now this winding 1 and winding 2, they are stressed by the voltage and also the thermal effect. So basically this is called as a multi-stress testing. Now the pictures for the entire setup, experimental setup, is shown here. Like these are the windings which are clamped by the steel bars and they are tightened by the screw. And in this they have kept these copper strips like outside by the epoxy insulation, and they are stressed by this steel bars. So this is a like cooling fans, and I'll show you the top view for this setup. Now this, so this coil 1, coil 2, coil 3, they are connected in series, and below the we are having a fans, and this side, like at this side we are having the voltage stress, and this is the split core transformer for the current effect, which will make a thermal effect to these coil 1 and coil 2. So these are some wires which are on the coil 3 this side, and this is basically for the measurement of the voltage, measurement of the temperature profile around the copper strips and insulations. Now I'll tell you the test procedure, like how this like this is the like solid lines. These are the temperature profile. Just check the only solid lights, this 1, 2, and 3 solid lights, not this red color. Just check this orange, blue, and purple kind of color. So these are the temperature profile, like it goes on increasing, like it's a process like when we are increasing the temperature from the ambient temperature from 40 degrees Celsius to 110 degrees Celsius. And this, it will take around 60 minutes, 65 minutes. And after that, at a certain limit, we will trip off the current transformer. Now the current transformer is shut down, and we turn on the fans, which will reduce its temperature from the upper limit to the ambient temperature. It will take around 30 minutes. So this heating up and cooling down is called as a one thermal cycle. Basically, this is called as a one thermal cycle, and I need to conduct, I mean, like around 1000, 3000, 4000 thermal cycles I have to conduct. So each cycle will take near about 90 minutes. So during this, in these cycles, like this dotted one is the temperature profile of the iron core, that outside that steel bars, which are like, rather than I should write it as steel bars rather than iron core. Like this is the temperature of these steel bars, that outside temperature of these steel bars, and that the dotted one, and the solid one is the copper temperature inside. These are the drilled thermocouples inside the insulation. So that's why this dummy coil is not stressed by the voltage. They are only stressed by the temperature. And this solid red color upper one, this is the another y-axis. This is for the current of the split core transformer. So showing that how if it is like near about 1500 ampere this side. So like this, and again it turn on, turn down, turn off, and again at this is the cooling time, and again it turn on, and again the temperature will start increasing. So this is the test procedure for the voltage profile. Along with this, I'm going to apply the voltage also. So this is a multi-stress. I'm applying the voltage for the voltage stress and also the thermal stress. So in this multi-stress, before I going to proceed this test, I need to conduct some tests, some non-destructive tests before I'm going to start any cycle. So at zero cycle, I'm going to use as zero cycle, and before applying any cycle, any one cycle, before I'm going up any one cycle, I'm going to conduct some tests. So those tests are called as a tan delta test, tan delta, and partial discharge. I'll explain tan delta and partial in detail in the next slide. So measure the tan delta and partial discharge parameters at zero thermal cycle. After this, we're going to conduct the 50 thermal cycles. with online partial discharge, like with the continuous partial discharge monitoring. And again, we de-energize the entire setup. And again, we're going to measure the tan delta and partial discharge experiment. And again, we keep on repeating this step. So we have to conduct 50 thermal cycles. After this, we have to go for a measurement of tan delta and partial discharge values. So now what is tan delta? Tan delta is also called as a displacement factor. Now, for a case of a pure dielectric, now what is dielectric? Like the material which we are using in our slides, like the material like this one is the material. So we in a high voltage, we called it as a dielectric material or insulation material. So for any pure dielectric material, we can represent this pure dielectric material in a form of electrical circuit. And any dielectric material between high voltage and a ground potential is considered as a capacitance. And in the capacitance, and in the case of ideal, they have a resistance value which is near about infinite. So which means that if resistance is infinite, then there will not be any leakage current or any type of current will flow through that insulation, because its property is to insulate, so it will not allow to flow any kind of current. So it definitely, if a resistance is huge, then it will resist to flow the current. So for an ideal case, this R is infinite. But in actual scenarios, this R is not equal to infinite. And if this R is not like let's leave this, like if R is infinite, then there will not be a no current in this side. And the entire current will be because of this capacitor. So that is called as IC. So in that case, this delta term is not in the picture. If R is 0, then this entire current will be shifted to this side. So then delta will be 0, and delta will be 0. So the tan delta is 0. It's a good thing. I mean, like we have to keep the tan delta value low, at very low value. So, but in actual scenario, this resistive component of the insulation is present. Due to that, there will be some IR amount of current will be there. And then the net vector sum of this IC and IR will be give to the IT. So due to that, the current drawn from the source will be much higher as compared to the previous scenario. So then tan delta will be perpendicular by base. So IR divided by IC. So if IR is huge, then tan delta value is huge, which means that if there is some defects, or if there is a like resistive, if the value is resistance is not infinite, then definitely IR current will be there, which will ultimately cause the tan delta. So we want tan delta value should be low. It should not be higher. So the setup for the measurement for the tan delta is shown here. So we have to measure for measurement of tan delta, we have to de-energize each coil and disconnect with the other coils, because we cannot measure the tan delta like connecting all three coils all together. So I have to dismantle everything and de-energize every coil, because then only I can measure the tan delta for this particular system. And at their end points, we have to kept some grounding guard wires, otherwise which will give you a like error in the measurement that will because of the ground currents. We only measure the currents because which is flowing through the insulation, not from the surface currents. So to grounded the surface currents, because at surface also, because during that measurement at surface also some current surface currents will also flow, which we need to keep them grounded, and we need to measure the currents which is only flowing inside the insulation, that is the leakage current. So after this, what do you mean by a partial discharge, another measurement? So I explained earlier, like any dielectric material is shown as a capacitance, but if there is a if there is a small void inside that insulation, so that void is having some gas, and that gas usually having a like breakdown strength which is less than the breakdown strength of the dielectric material. So that is also shown in the form of electrical circuit. Like if there is a small void here, and so that void is having some gas inside it, so that will also represent by a capacitor. So that void is represented by a Ca, and the the material which is present in series with this void, the material which is present in this void side will represent by a CB, and the remaining which is having a remaining the test object which does not have any kind of a void, that will represent by a CC. So CC is the remaining void free insulation of the test object. CB is the capacitance of the remaining series insulation with the void, and Ca is the capacitance of the void inside the insulation. Now, whenever the breakdown of this inside of the material inside this void is the it reaches at its breakdown value, then in electrical circuit we represent by a spark gap, and then there will be a spark at this point. Then this capacitor will be short circuit. So the all the charge which is present inside this will pass through this, and that will cause a current to flow in this circuit, and that current we will measure in the form of this, so by the oscilloscope and some measuring instrument, and that current will give us the amount of charge, because that charge is equal to that integration of current with respect to time will give the charge. Now this is the way to measure the partial discharge of that is the way to measure the charge present inside that void. Now this is a direct method, but we cannot measure directly. So for this, we need to connect some external. This is now this is the test object. The object which I'm going to test is having some void inside this. Now to measure the amount of charge inside that void, we need to keep one coupling capacitor with outside externally coupling capacitors. The one which I have shown in this picture. So these are the coupling capacitors. And why I'm using two? Because for each coil we have to measure the separately partial discharge. And using this filter is to is purpose of using this filter is like there will not be any interference of the measurement of this with this filters. So they have a separate measurement of stator coil, and stator coil second having a separate measurement. And they further they having some quadrupoles and PD detectors. So coming back to the partial slide. Now this coupling capacitor is connected with the ZM, like that is the series impedance to protect the system. And this also a series impedance also to protect the high voltage source from because there should not be any interference with the input signal and the signals and the signal of current from coming from the discharges of these capacitors. Now what we are doing is like we charge this capacitor at a particular voltage or at the rated voltage, and if there is any void inside this capacitor or void inside the insulation, if that void get discharged, so then for that discharge the amount of charge again, I mean once it is discharged, now again it will again start charging that void. So for charging of that void will take place by this capacitor. So at that time the amount of charge will be transferred by this capacitor to this capacitor. So indirectly we measure that amount of charge when it after discharge again it will giving the charge back to this capacitor, this voids to charge again. So we measure indirectly the amount of charge from this capacitor externally. So that will give the idea that these are the voids which are present inside the insulation, and we measure the amount of that charge. Now based on that charge we try to find out that what are the type of defects are present inside the insulation, like it is because of a small void, or it is because of the gap between delamination, or because of the abrasion. So for this we make some standards by artificially creating the defects, and take the data and make a standard that for this type of defects, if this kind of patterns are coming, then there might be a chance of this type of defects present inside the insulation. So the setup for partial discharge is shown here. These are
Sorry,
the two.
Virendra.
Yeah, sure.
We have few minutes left. So
Yeah, just
max 10 minutes. So I think we have to move away from the technical now and towards the results.
yeah. The next slide is
Right?
the results only. Yeah.
Perfect. Thank you.
So thank you, Patappa. So this is the partial discharge setup. This is a coupling capacitor 1 and coupling capacitor 2. Now the results obtained from the tan delta, this is shown here. This side is the backup coil, the coil which is used as a which is not in use, but they are manufactured at the same time, and this is the service coil. So now I have connected 0 cycle, 50 cycle, and after every 50 cycles we have conducted the tan delta measurement and partial discharge measurements. So 50, 100 and 200. So the due to like they have kept in a for a long period of time, they have kept inside the like at a storage place, and due to that time they have a moisture content inside them, and that will clearly justified by observing the tan delta values from the initial from 0 to 50 cycles. Their values are quite higher. It's near about 7 into 10 to the power minus 3, that blue and orange color for initial cycles. But as we keep on increasing the cycles, that moisture content has evaporated and this tan delta values keep on decreasing. So similarly, this kind of pattern we have observed that like from as the number of cycles are increasing, the tan delta values are keeps on decreasing. But at higher potential, this tan delta values are little bit higher. But if we compare this backup coil with the service coil, which is already in the service, we found that its tan delta values are much higher for that 200 cycles. Like it's because their value are not increasing as the cycle number of cycles increasing. At higher cycles, their tan delta is keep on increasing, this green color. So at higher potential also, we observe the higher value of tan delta. The another results obtained from the partial discharge is like this. This yellow color is for the temperature profile, and this from 0 to 4500 minute is like a temperature is a time of the 50 cycles. Like each cycle takes 60 minutes. So basically these are the 50 cycles, and orange color is for the backup coil and blue color is for the service coil. So backup coil initially shows this kind of trend that this PD values are increasing and then it keeps on decreasing. So this is because like at few initial thermal cycles, because of the moisture content and the dynamic behavior of the voids present inside the insulation will cause a sudden increment of the partial discharge values. So these PD values are basically charge, that amount of charge are discharges. Usually the limit that acceptable limits are 100 picofarad to 200 picofarad. But if it is coming near about 1 nanocoulomb, it is a huge amount of charge. But initial cycles we observed this one, but later stages we found that this it start disappearing. So after 50 cycles, we found that this amount of charges are disappearing for the case of backup coil and also the service coil. Now this kind of behavior is like maintained till 100 coils, but after 100 coil after so not 100 cycles, we observe that in the like in the case of 160 cycles, the service coil which is already in the service, their amount of PD values start increasing, and it shows a uniform kind of a pattern, like which in which it is keep on increasing like this. These are the blue colors line for the service coil, which are continuously increasing till 200 cycles. And after 200 cycles, again we have tested the tan delta values and we found that the tan delta values are also much higher, which gives an indication that there's something is happening, like or maybe the amount of defects are increased inside the insulation. And after 200 cycles, what we observed that which was very much clear from these observation, we show that after 200 cycles, we conducted the experiment and there we found that the breakdown of the service bar at this point. I mean, if a needle like needle kind of a 1 micron or 2 micron level of gap is there, then that gap will be a problem for the insulation and it will ultimately break down the machine, because this level of the 1 micron or 2 micron level of a crack is inside the material will cause the carbonize of that channel and ultimately lead to the breakdown of the machine. So these are the PDIV values. PDIV values are basically the partial discharge at the point at which the partial discharge just inception volt. These are the inception voltage of the partial discharge. So these machines are rated for the 1.9 kV, line to ground voltage is 1.9 kV, and for the service coil we found that these values are much lesser as we increase the load cycles compared to the backup coil. So this will give an idea like how this PD values and the tan delta values give an indication of the indication before the failure of any insulation, any hydrogenator stator insulation. So what are my future work is I need to conduct the 3000 thermal load cycles and investigation on the PD patterns for a better understanding of the aging of the hydrogenator stator bar, and the also comparison of the load cycling with the high voltage for backup and service coil, which will be like interest for the standardization bodies, as this will address the relevance of the existing standards, because in existing standard they are not considering the multi-stress testing. So that's all about this presentation. Thank you so much. So,
Perfect. Thank you very much, Birender.
thank you, Patoka.
If you have any questions, you can raise your hand and I'll allow microphone for you, or you can write it into the chat. While we are waiting, I could ask if you then find out something, or what's the takeaway to the industry for us from your research?
Yeah. So, like Patoka, usually in industry scenarios, we usually conducted the partial discharge measurements, and during the manufacture time also, we try to kept the coupling capacitors already placed inside the hydrogenators in the manufacturing. And by observing the data, we can, if we found these kind of data, we can claim that there might be a chance in the further few days, like there might be a chance of a breakdown of the insulation. So we can plan a maintenance for that particular hydrogenator rather than going for a suddenly breakdown of that hydrogenator station. And these further, like 10 delta values will give you idea about the number of defects or amount of defects are present inside the insulation, which will also helpful when we go for a replacement of the replacement of the old or service bar with the fresh bars. And before we going for a replacement, we need to conduct these type of tests also.
Very good, thank you.
Yeah.
You as well showed pictures from stator and rotor from, I assume, Norwegian hydropower station.
Yeah.
Did your research suggest something for this particular site? Did you find out some issues, some breakdowns to happen?
I mean, like from that site, I observed that this is generally because of the placement of these stator bars inside these slots, and at the end points, we usually find that the gap between the nearby bars are quite less, and which will ultimately cause the bar to bar breakdown or the end points, because these are the points where the electric potential is quite high compared to the center part. At the end points, the gap is also very less, and which cause the bar to bar discharges and ultimately lead to the breakdown of the insulation. So for that, we need to keep end winding insulation to be more like regular testing for that end windings, and also we need to take care about the there is a layer which we usually use in the end winding sites for the because at end winding points they are having because of the turning of that stator bar will cause a huge amount of electric field stress at that particular point. So there we need to keep the stress grading kind of tapes we usually use for the protection of the stator bars at the end sides, at the end winding sides. Yeah.
Do we have any questions from the participants? No, I think everybody seems to be happy, so hopefully you explained well.
Yeah.
The problematics. Then we can say thank you very much, Birender.
Thank you, Patoka. Thank you so much. Thank you once again. Thanks to everyone.
And I hope you'll come next month for the next postdoctoral researcher.
Yeah, definitely, definitely.
Thank you very much.
Thank you, Patoka. Thank you so much. Thank you, everyone.
Have a nice day.